and I thank Andrew for referring to me as a pioneer, but I must say I wouldn't have even gotten into optical SETI had it not been for Dan having brought Charlie Towns to a meeting of the thing called SETI 2020 that was held 20 years ago, I guess, in which Charlie really basically changed my view of optical SETI. And let me share screen and just launch into this. So let's see, I got to find the right window here. I guess it's going to be this one. And then I have to launch the little wine glass here. Okay, are you guys seeing the screen okay? Yeah.
Yes.
Okay.
Yep.
All right, background on theory. I'm not sure theory, I put some quotes around it, but anyway. You know, when you look back in the history, how do I get this thing to launch? Okay. Remember the famous 1959 Kekkonen-Marson, and they say, where should we look? Of course, 1420, that's really the right place. Everybody knows about it, blah, blah, blah. And, you know, they got into this in a funny sort of way. They had a new particle accelerator at Cornell, and Kekkonen, I guess, waltzes into Morrison's office and says, hey, do you think we could launch a beam that could reach, you know, another planet out there? And so they went and looked through the whole spectrum, and they decided that it should be in the radio waves. And the reason is, and they go on about this, that in the optical, it's basically too difficult to make powerful beams, and the photons cost too much and all that kind of stuff. Of course, this was 1959. Let me just say this thing here, which is, you know, there's this other window. There's radio, which is where SETI's traditionally been done, but there's the optical window. And this comes from one wonderful little talk by Ed Purcell, which if you haven't read it, you really should. It's the Brookhaven lecture, a little hard to come by. I could send a PDF of it to the participants, I guess through John, in case anybody's interested. He talks about radio astronomy, how terribly efficient it is with just tiny amounts of energy. He points out that in the 9 years since the 21 centimeter line was discovered, he doesn't say that he discovered it, but anyway, he and Ewan did, that less than an erg of total energy has been accumulated by all observatories on Earth. And with this, they've mapped out the galactic arms. Really quite an astonishing thing. And then he says in this wonderful way, I just love it, the way Ed Purcell says things. He says, a more astonishing figure is one that I had to compute 3 times before I was sure of my arithmetic. The total energy received by all 21 centimeter observatories over the past 9 years is less than 1 erg. From less than 1 erg of energy, we have built this picture of our galaxy. And then I love this wonderful line that dates the era. Most of you know what an erg is. You can't knock the ash off your cigarette with an erg. Of course, most of us don't have a cigarette to knock an ash off of. Ed had a wonderful way of seeing things. I remember another one he used to say, which sort of expressed the Fourier duality. He'd say, if you play a 30-second note on a tuba, it doesn't much matter which note you play. I thought that was wonderful. Anyway, so Ed talks about the efficiency of radio communication. Then he talks about the inefficiency of space travel, you know, large amounts of energy, long travel times, et cetera, et cetera. But then he loops back around and says, but we can use the sufficient radio communication to communicate. We don't have to go there. It's a wonderful little thing. And he ends with a wonderful little enthusiastic thing about SETI, which I just loved. Anyway, this is 59, where Kekkonen and Morrison are saying that it should be in the radio wave. He says that near visible require very great power, complicated techniques, and so on. However, this was the year before lasers were invented. Here's 1 year after lasers are invented, Schwartz and Towns, pointing out that we have these maser oscillators. Towns never liked the word laser. I think he got into a fight with Gould over that. But anyway, he's talking lasers here. And of course, lasers since 1961 have become quite powerful. Here's Charlie Towns in 1983, I believe it is. Yeah, 1983, talking about what is the best wavelength. And he says, you know, people have often thought about the microwave region and so on. But he said that if generalized types of detection are considered, in particular amplitude photon detection rather than linear heterodyne detection, and if you take advantage of the directivity of telescopes, somewhat less power is required at infrared than at microwave. And, you know, it sort of depends on other parameters, like whether you can build large apertures and all that kind of stuff. So I think, do I have a little pop-in? Yeah, I have a little thing here just showing you. Is this being covered by, can you guys see the whole equation there, or am I being covered by my little gallery here? I'm going to kill the gallery.
It's all there.
We see it.
Oh, they're good. Okay, well, you know, the gain of Arecibo, when Arecibo was alive, is about 70 dB. The gain of Keck at a micron is a diffraction limit. It is 160 dB. You know, that 90 dBs is nothing to sneeze at, and it makes up for a lot of inefficiencies in the photon energy and so on. Anyway, so that's interesting. And it was Charlie talking at this 2020 conference that really got a bunch of us interested. Then you talk about, well, what actually you're going to communicate. And here there's an interesting difference between what you do at radio and what you do at optical. And I want to move this thing out of the way. I just want to point this out because I think to many of us, it was surprising. At radio frequencies, you know, pulses are kind of a mess because there are a lot of cultural natural pulse sources, you know, sparks and things like that, and lightning strikes and everything else. And pulses are dispersed by the dilute electron gas in the interstellar medium. On the other hand, at radio frequencies, a stable oscillator is a nice single spike in frequency domain. You can use coherent mixing and integration to narrow your effective bandwidth, and the interstellar medium does very little broadening. There's a little bit of, you know, turbulent multiple scattering off of ionized clouds and so on, but people like Cordes and Lazio, and I think earlier Drake and Helou had done some calculations that showed that for typical path lengths in the galaxy and in typical frequencies like the 21 centimeter, the 1420 megahertz, you're only talking broadenings of order millihertz, which means you can really, a narrow line just stands out. There are no natural sources of that. At optical frequencies, things work quite differently. First of all, there's huge Doppler shifts you see down here. A kilometer per second is just 5 kilohertz at the 21 centimeter line, but it's a gigahertz at a micron. You know, we're talking petahertz frequencies here. On the other hand, pulse dispersion is entirely negligible. You know, it goes like f to the minus 2, 1 over f squared. So from going to a gigahertz to a petahertz, that's 6 orders of magnitude. When you square that, that's 10 to the 12th times less dispersion. So that's completely negligible. What does happen is there's multiple scattering off of grains. I'll talk just a bit about that later. Jim Cordes has done some nice calculations of that. However, pulses are really quite viable at these frequencies. You can't make ultra narrowband filters, and coherent mixing does produce these large Doppler shifts, so you can't really take advantage of narrowband receivers. And also, Towns pointed out, although I've never seen anybody really do this calculation carefully, but I'll bet somebody on this call can, which is that there's an inherent noise source when you do coherent detection at any frequency. The fact is that by doing coherent detection, you know the phase, and so that introduces a quantum amplitude noise. And at radio waves, this is negligible, but at optical frequencies, it's dominant. And so you don't actually want to do heterodyne detection. You want to do just amplitude detection. So Charlie made the point that in the optical, you might want to look for a spike in time, or you might want to look for a spectroscopic spike. And he actually favored the infrared. Okay, well, let me move on here. Let's see, have I lost my cursor? Yeah. So this is just, I just want to sort of fold this in. We had actually it was sponsored by Breakthrough 5 years ago in the summer. And about a dozen of us got together, there's some names at the bottom, just to look at this business of optical SETI. We felt that Breakthrough had been ignoring what we called the missing corner. They were doing, and still are, spectroscopic searches with APF, but they were not doing pulse searches. They were looking at pulses and carriers in the radio, but in the optical, only carriers, so to speak. Anyway, I'll just pull a few slides out of this one. Again, as I've said, well, there are sort of two things going on here, which is that if you do searches just targeted at individual sources, you have extreme intermittency because you're only looking at one thing at a time. You have lack of surround context if you're looking at individual stars, let's say, for instance, spectroscopic stuff. And you also neglect all the things that are in between the stars. And there's plenty of reason to believe that civilizations, post-biological civilizations in particular, don't really care much about planets. In fact, they probably hate the gravity and would rather be in between. So there's reasons to look at other places. So what are needed, and I think Jill Tarter got me into this business, is wide field and long duration. As she put it, all sky, all the time. And this can be done now was 5 years ago, with detectors such as PMTs or more conveniently solid state photomultipliers for looking for pulses. And maybe perhaps high resolution spectroscopy as well, and maybe some combination. And then, as I've said here before, that you have to worry about free dispersion, but here you don't. And pulse lasers are quite practicable, and I'll show you some numbers here, but basically with petawatt pulse lasers or megawatt CW, these things are fully detectable at interstellar distances. And let me skip through this because, well, just to say at the bottom here that it may be that the right place to be is in the near infrared. Near infrared is kind of problematical because of detectors and because of basically higher background levels from thermal radiation. But the galaxy becomes rather transparent at 10 microns. Stars are dimmer and photons are cheaper. A lot of good reasons to go there when we have the ability to do it, probably from space. 4 ideas came out from the workshop. These are pulsed optical SETI. One was and you'll hear more about these today. One is basically an all sky, very large area dispersive search. So it looks both for spectroscopic features, but also for time variation. This work is being done by Elliot Gillum, the SETI Institute. Large sky, what we call large sky, thousands of square degrees with nanosecond type sensitivity. This is now being carried out with PanaSETI. Also an infrared component to that. And then finally, gamma ray telescopes, Cherenkov telescopes, stuff like Veritas, and so on. Okay, this was out of the, and by the way, if people are interested, this workshop report, I think, was only sent to Breakthrough Listen and the few of us who are on that. If other people are interested, I'd be happy to just send the PDF of that report to John. He can distribute it if people are interested. So you're just summarizing, for directed communication, you get a lot more gain. When I calculated this 10 years ago, I got 150 dB, but when I did it last night, I got 160 dB. So we gained 10 dB by recalculating. The absence of dispersion. There is, however, scattering by grains, and optical radiation is scattered by grains of wavelength size. However, there's an unscattered component, basically ballistic photons that slip in between the grains, and out to a kiloparsec or so, about half the photons come through unscattered, and therefore at their natural transmitted pulse width. Lasers have gotten better. Of course, optical allows you to have much greater bandwidths if, in fact, we can get an optical link going. And they can be much simpler to detect because you're simply looking for a pulse. This is just a picture, a graph by calendar year of the total of the most powerful lasers on Earth. These are units of terawatts, by the way. So we go from a terawatt to a petawatt here. And this is the point at which they started doing pulsed diode pump lasers, and they got up to over a petawatt back in the 90s, albeit for a fraction of a nanosecond. Just for this instantaneous power, by the way, is a lot more than the total electric power generation on Earth. I drew a graph here based on 2 data points, one back here and one over here on this log linear graph of total electric power generation in the world. This is the California energy crisis. Remember that thing? I just sketched that in. The idea is lasers have gotten quite powerful. And this is actually just some components from the first optical search we did at Harvard, a targeted search looking at a few thousand nearby stars. This is the paper by Howard et al., which I think is worth reading. It reports on the search we did, but since there hadn't been really much written about optical SETI in the literature, we basically spent a few pages just talking about some of the basics, and just the first part of the abstract here discusses that. But let me just go to one of the paragraphs within it, which is a possible transmission scheme. And here we say that we calculated a particular scheme. We chose the most powerful laser on the drawing board at the time. It was basically a 3 nanosecond petawatt. See, actually I have the real numbers here, rather more than a petawatt. 3 nanosecond, 4.7 megajoules, so a little over 10 to the 15th watts for 3 nanoseconds, and it pulses at 10 hertz. It was intended to be used for confinement, inertial confinement fusion power plants. We imagine one of these on a planet orbiting a star 1,000 light years from us, and we and they both use 10-meter Keck telescopes. They transmit it, we receive. The transmitted beam is pretty small because you're talking a wavelength of a micron and an aperture of 10 meters, so you get that ratio, which at 1,000 light years illuminates a 6 AU disk. That's pretty good. It does the habitable disk. Now, here's the interesting thing is that the number of photons received is actually quite large into our aperture, 1,500 photons in one of those pulses over that 3 nanoseconds. I got an email just a few weeks ago from someone in England saying, that's a nice equation. How did you get it? So I wrote her back how you get it, and I'll just show you because it's kind of fun and easy. Here's how you do it. You imagine and the simple, cheap, dirty way is here's our transmitter, here's our receiver, here's our distance. The beam, ignoring factors of order unity, the beam is the ratio of the wavelength to the diameter. Okay, so the illuminated disk has diameter theta times the distance. So the fraction received is that the diameter of that disk over the diameter of the receiver over the diameter of that disk all squared, which works out to be dTdr over lambda r. If a number of photons sent is just the energy sent, you sent megajoule divided by h nu, that's the energy of a photon, and converting to wavelength, you get this. So you stick it in and here's your answer. The received number equals that. This is equation 2 of that paper, except for some nasty little factors, and the factors come in this way. There's the extinction, which turns out to be not too bad at a micron in 1,000 light years. And the pi squared over 16 comes from using the correct expression for antenna gain, and here's how you do it. I won't bore you with the details. So here's the deal. Here's this little system with the 2 Kecks, 1,000 light years apart, and here we're transmitting this 5 megajoule pulse, 3 nanoseconds long, and here's the number of photons, and here's the correct factors. Now you might say, well, you're looking at a star, isn't that going to blind you? No, not hardly, because we're only talking nanoseconds here. The background is about 0.03 nanoseconds, 0.03 photons per nanosecond. That's about 1/10 of a photon during the time of the laser pulse. So we have 1,000 photons from the pulse and 1/10 of a photon from the star. We have a ratio 10 to the 4 laser flux to stellar flux. This is a flash that you can see. No question about it. I got 10 minutes left. I'm going to zoom. There's a couple other things you need to worry about. You need to aim this thing right, and you need to lead the bird because we have proper motions. So you can calculate easily enough what it takes. And again, adopting this 1,000 light year range, where we have something like 1,000 sun-like stars. And nowadays we know that they have probably 1,000 habitable planets going around those things. So it turns out that the numbers are, you have to know how to aim within 33 milliarc seconds, and you have to know the proper motion to 33 microarc seconds per year. Why micro? Because 1,000 years, that's going to be 33 milliarc seconds. This is what corresponds to a 10 AU aiming accuracy. The other amusing thing is you need to know the range, because you need to know how long it's going to take to get there because of this proper motion. And it needs to be, in fact, quite accurate. A surprising result here. You need to know within 5 light years if it's at 1,000 light years. But we assume an advanced civilization probably knows that, can probably figure out how to do astrometry to that kind of accuracy. Okay, let's see. So I just show this because this was some topics that were in our report, including some appendixes here that are like 10 pages long. I have some interesting details. I won't go through any interesting details here. Moving right along. This is a table out of the report. And what I've done here is just for 4 different systems that we talked about and some 3 existing systems, I've highlighted several different parameters here, and in particular, made in bright green the ways in which they excel. The gamma ray telescopes have huge sensitivity because they have big apertures compared with custom systems. Infrared, of course, you get into the infrared. The gamma ray scopes are particularly good, again, on how much energy it takes to transmit because they're very sensitive. The time resolution is really good for these systems that basically use nanosecond speed detectors. The wide field Elliott Gillam's laser SETI is superior in terms of sky coverage per scope. Some of these involve distributed scopes like the PanaSETI. It's 160 per scope, but we're going to have 100 of those. So that compensates some sense. Here's a picture of the first search we did at Harvard. This is just a piece of history. I'll skip through it. Just to point out, however, that we did co-observe with Princeton for 2 years. In our 5 years at Harvard, we got something like 130 or 140 candidates, never repeated. When we co-observed with Princeton, we got 0. It really makes sense to co-observe with distributed sites, particularly if you don't want to have any nasty signals to have to worry about. Here's a little observatory system that we built to do our first so-called all-sky search with photomultipliers. This is Andrew Howard down here. Here's Andrew and Curtis, and here's the sky that we covered with this transit search. I won't say much about this. I want to move on to the new things in the remaining 7 minutes. These are the detectors that have become interesting now. These are so-called solid-state photomultipliers or silicon photomultipliers or multi-pixel photon counters. All those names mean the same thing. They're very fast. We're talking nanosecond speed. They're reasonably large area. You can get them in 3 millimeters up to 6 millimeters square as individual pixels. Each one of these has 10,000 or so micropixels. So they're proportional. If you have a bunch of photons that land on one of these macro pixels, the pulse that you get out will be proportional to the number of photons that hit. That gives us the ability to distinguish bright flashes from dim flashes. And here's a little oscilloscope trace, a couple of them, just to show how good these things are. This is just time versus amplitude. This is a 2 microseconds per vision. Just capturing here some examples of single photons. See, those are those heights, 2 photoelectron, 3 photoelectron. Very nice and linear. And they cost about $3 a pixel. Very, very nice, compared with $1,000 a pixel for a photomultiplier. And here's just a longer, a span here, just showing that if you just let this thing run, you get very nice uniform pulse heights here. These are 2 photoelectrons. These are all single. All right. This is OSETI. Shelley Wright's going to talk about this tomorrow. Nothing much to say except that 2 observatories, and we're not using mirrors. We're using Fresnel lenses. This idea was suggested by Jerome Mayer at UCSD, and it really makes a lot of sense. You don't need high resolution. You don't need diffraction limited. What you want is aperture and cheap. Here's some OSETI hardware. I'll just zip through it. It's a circuit board with 4 panels of these things in a corner, and then you can abut the corners to make 16 panels. And this is the current hardware being tested at Lick. There's Shelley. Here's a nice nighttime picture without Shelley. This is scared of the dark. I just want to spend in the last 5 minutes a quick run through of some future stuff and some interesting other stuff. Here's Elliot Gillam's laser SETI. This is a very clever application of a wide field camera using an overclocked focal plane. And it took me a while to figure this out, but I finally figured out. Here's how it works. You have a 3,000 pixel square fast shifting focal plane, and you shift the thing out super fast. You overclock it. And so each row coming down is the average of everything. It sums all the photons that hit it as it comes down on this thing. And here's what you see. If you had a star somewhere, that's persistent. So you'd see the star in its spectra. If you had a hot pixel, you'd have the pixel, but no spectra. If you have, here's some stars again. If you have a laser that flashes a few times, you'll get intermittent things with the 2 laser lines symmetrical about the center. Very, very nice idea. It's low sensitivity, but high field, and does a nice job for occasional things that are bright. Here's a couple of pictures that Elliot sent me. You'll hear from him later. Then there's the business of the Cherenkov arrays. Here's the Veritas array. We'll hear more about that. And here's the upcoming CTA array. This is the Southern Hemisphere picture I found on the web to look for flashes. Of course, they're interested in flashes from gamma ray events. They at least in Veritas, they filter out things that are only in a single pixel because Cherenkov events are spread out, but one can fiddle with the triggering and make something that's good for SETI too. Let me just go through a couple last things. Infrared is a better place, or Charlie was right all along. He was talking about 10 microns. And this comes from Jim Cortis's appendix in the back of SETI 2020, in which he worries about what happens when optical pulses go through the galaxy. And what happens is they get scattered from particles, but the scattering is very wavelength dependent, at least lambda squared. So what happens in the visible is that you get a lot of scattering, and out to a kiloparsec or so, you're starting to get into trouble. You have no hope of seeing the center of the galaxy. But at 10 microns, you do quite a bit better. that's the reason to go there. Here's a picture of the transmission just from Allen's astrophysical quantities. Even at a few microns, you're doing pretty well at a kiloparsec, as you can see. The other thing is you get more photons for your buck. The number of photons go as lambda for a given laser power, but the black body falls off really rapidly because you're on the backside of these curves. And depending upon whether you go with constant delta nu or constant fractional width, you gain in the ratio of laser photons to stellar photons by at least lambda squared or lambda cubed, depending upon your system. So infrared's the place to go. It's hard to make detectors. They're expensive. To get fast sensitive detectors, you pay $1,000 a pixel these days, but that may get better. Here's a couple other ideas that I've been looking at, and they look quite interesting. Maybe we'll hear about them today. One idea is the idea of coherence. You know, lasers basically make a sine wave, whereas black body radiation or spectral lines can make a very narrow line, but it has full-size fluctuations. A filtered black body or spectral line is completely different from a laser that's jittering around with the same bandwidth, because the laser has more or less constant amplitude and the other sources go through full amplitude fluctuations. So you look for coherence here, and the idea here is to use a Mach-Zehnder interferometer and wiggle back and forth the path difference and look for fluctuations in the amplitude. And if the path difference is long enough so that natural sources don't have that coherence, you won't see amplitude variations. But for laser signals that have that much coherence after surviving through the atmosphere, you will. A very cute idea. Here's his conclusion. I only have one more minute. I guess these slides will be up so you can look at his conclusion here. Here's another idea from Hipke talking about quantum types things that you might have squeeze states, or you look for higher order correlations in the photon field. Interesting stuff. This business of higher order correlations goes way, way back. I think Roy Glauber was the one who first really founded the whole science of quantum optics and talks a lot about higher than second order correlations and how these fields are particularly distinguished from other kinds of fields. And this could make a lot of sense. Particularly if there's a civilization that seriously uses quantum communication. There's always the question in both of these schemes whether it would survive coming through the atmosphere, and in particular for the business of this, it would be pretty much damaged by the fluctuations, the twinkle, the scintillations. So you'd probably have to use adaptive optics or go into space for that. But hey, the sky's the limit. And here's the last thing I have to say in my last half a minute, which is that from Martin Harwood comes this idea of photon orbital angular momentum, that you can make a twisty kind of field. And it looks different from plain old ordinary photons. And this might be an interesting way to communicate. In particular, you can put extra information into these higher orbital angular momentum modes. I don't think anything has been done to follow up on this, but perhaps we'll hear more about this today. Just my final shot here is that if anybody's interested in that 2016 workshop report, I can send it to John. The Cordis appendix at the back of SETI 2020, it may also not be widely available. I can scan that and send it as well. That's all I have to say. Thank you all.
Thank you very much for the very enlightening talk. And it's great to see lots of projects and ideas that trace back from the very beginning. And